we want to reason out the situation where we know VF, delta T, and A. So we write out our variables and we circle VF, A, and delta T because they're known, and maybe just to make it perfectly clear, I'm correlating those with a red or pink circle, whatever this color is. There we have it. And we also write our basic triangles, the one that corresponds to the definition of average velocity, average acceleration, the information we get from the straight line graph, and the definition of delta, this sneaky thing that we kind of slip in here, but it's not really necessary because delta does have a very well-defined definition. Okay, so we know VF, A, and delta T. What can we do? VF and A, well, VF appears here and here, doesn't appear over here, doesn't appear with the acceleration anywhere. So VF and A can't be reasoned out directly, not from this information. VF and delta T don't appear together anywhere, and there are good reasons. VF and A, final velocity and how quickly the velocity is changing doesn't tell you much of anything by itself. Now, if you happen to know the acceleration of the delta T, then you can find how much the velocity changes, and you can put that with VF and do quite a bit. Anyhow, VF and A don't help, and VF and delta T don't help, so we'd better hope that A and delta T does. Well, I just referred to how it does, but we can see, first of all, that they're together in this triangle. Second, we can ask ourselves, well, why should they be together? Well, because the definition of average acceleration is average rate of change of velocity with respect to clock time, and that's delta V divided by delta T. So these three appear because of the definition of average acceleration. We can connect these three, meaning if we know any two, we can find the third. So we can find delta V. So we can indicate that, and let me use a different color here. Okay, so now we've got delta V. Now what can we do? Okay, well, if we know V and delta V, delta V and VF, in other words, final velocity and how much the velocity changes, well, we can figure out what the initial velocity must have been, subtract the final velocity from VF. So we're going to be able to get the initial velocity. And of course, that's the way I've got it written down here. Delta T and A give us delta V. And here's why: definition of acceleration, A equals delta V over delta T. VF and delta V give us V naught, meaning of delta. Delta V is VF minus V naught. Okay, delta V and VF give us average velocity. Okay, and that's very straightforward. That's just because of the straight line graph. We can average the final and initial velocity to get the average velocity. And then delta T and V bar give us delta S. Okay, let's just circle. We got V bar. So we put V bar together with delta T, we get delta S just because of the definition of average velocity. And of course we see delta T and delta S, delta T, V bar, and delta S in a triangle up here. So that all works out. Now, specific numerical example. If VF is 30 meters per second, delta T is 4 seconds, A is 5 meters per second squared, how does this reasoning process work out? Well, again, A is delta T over delta V, delta V over delta T, so that delta V is just A multiplied by delta T. We just multiply the acceleration by the time interval, 5 meters per second squared by 4 seconds. And you think 5 meters per second squared means 5 meters per second every second. Multiplied by 4 seconds, we get 20 meters per second. And of course, the units work out as well. Meters over seconds squared times seconds over 1 gives us meters over seconds. Then we follow with delta V. Since we know, well, we follow with the definition of delta. Delta V is VF minus V naught. We know delta V, and we were given the value of VF. So we do the VF minus the delta V, 30 meters per second minus the change 20 meters per second, so we must have started at 10 meters per second. Now that we know both initial and final velocities, we very easily find the average velocity, the average of the two, and that's very straightforward. That turns out to be 20 meters per second. Just coincidence that this number and this number are the same in this particular example. And then to get the last thing that we need, the delta S, which we listed here, we just use the fact that V bar is delta S over delta T, which comes from the definition of average velocity. And delta S is V bar delta T, 20 meters per second multiplied by 4 seconds. Now, you recall, if you've been watching these in sequence, that this is just something that was left over from the previous analysis, and we don't need it here. So that's it.